Kirchhoff's current law, sometimes shortened to KCL, is a statement about current in a circuit that says the algebraic sum of current entering and exiting a node is zero. The same amount of charge is always entering a node as it is leaving. To explain why this is true, we need to think back to the definition of current. Current is the amount of charge, a coulomb, passing through a circuit over a specific time, a second. Electrically, we talk about the movement of positive charge, which are positive ions, or the holes resulting from the absence of free electrons moving in the opposite direction. So current is a defined amount of charge moving, and like all measurable quantities, obeys the laws of conservation, so that none may be created or destroyed in a system, ignoring things like current sources. This means that all the current approaching a node has to also pass and continue away from that node. Current also cannot stop or slow or speed up differently along a circuit because charges affect each other and have to move at the same speed through a length, like tight traffic. This law is extremely useful and explanatory in parallel branches. The current entering a node is the same as that leaving, regardless of the number of branches on either side. The sum of the current between all branches entering versus leaving is the same, the average current in a branch being less if there are more branches in that direction. This can be compared to the number of cars passing a point after a road splits, assuming the cars retain their speed, because the same amount of cars moving on the original single road had to divide to more sparsely populate these vacating road, like charges. Here's an example of Kirchhoff's current law. Say we know the current in a circuit approaching a node and the current in one of two branches leaving that node, talking in the direction of current. If the entering current is 7 milliamps and the current we know leaving is 5 milliamps, we know from Kirchhoff's current law that 7 milliamps is equal to 5 milliamps plus the current in that other branch. We can calculate the answer 2 milliamps, and this type of problem can also be solved with current in the other direction. Paired with Kirchhoff's voltage equivalence of this law, Ohm's law, and an understanding of circuit components, we can solve for many values from very little information, making it extremely useful. Thank you.